Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video lesson is going to just be a really quick run-through of some of the separation techniques that we're not going to actually have time to cover, but I want you to at least be familiar with vocabulary. So we're going to start with a couple of topics out of Chapter 12, which was liquid-liquid and fluid-solid separation processes. The first of these topics is the single-stage liquid-liquid extraction processes, and frankly, you are supposed to be covering this in your staged mass transfer course. So the idea here, though, is that you have two liquid phases, and if you have two liquids, you need to keep them in contact, so that creates a challenge. Also, that these phases typically occur, usually we think of them as occurring with a three-component system that may be represented as a triangle diagram. And you've looked at these, say, with your mass and energy balance textbook. You're doing this when you have temperature-sensitive materials often, or if you have a solvent that will selectively dissolve one or maybe just a few that are desirable to keep together of the components from the feed into this second phase. And so liquid-liquid extraction is an important process, but we will not be really addressing it here. The second topic out of Chapter 12 is liquid-solid leaching. This is essentially just liquid-solid extraction. It is mathematically similar to liquid-liquid extraction, which is similar to, say, distillation or absorption. But here we're adding a liquid to a solid in order to remove one or more of the components from that solid. Generally, in order to do this, we reduce the particle size as small as possible so that we can make the separation easier. This is frequently going to be used for metallurgical processes, so think of like gold ore, something like that, or for food processes. Of course, my favorite there is making coffee. And the primary distinction between this and liquid-liquid extraction is primarily the difficulty of handling the solids in these systems. Next, we're going to jump into Chapter 13 briefly, which is membrane separation processes. This is really a growing area for engineering separations. They're going to use either microporous or non-porous membranes as a semi-permeable barrier. And this can be used to do some of those really difficult or very highly selective separations. So maybe it will only take one component and allow it through. Now, we've talked a little bit about porous and non-porous solids earlier in the course when we were talking about diffusion and when we were talking about drying. The non-porous membranes are going to be useful when we talk about osmosis or reverse osmosis. The primary application there is desalination of seawater. Pervaporation, which is useful in separating azeotropes, or gas permeation, which is one application is hydrogen enrichment so that you can move hydrogen into a very pure gas phase. Then we have microporous membranes, and these are going to actually have pores that go through them, but they're very, very small and sized for specific families of molecules. Here, our primary processes would be dialysis, microfiltration, or ultrafiltration. And as you see listed here, dialysis, typically we think of this in terms of hemodialysis, that we're removing impurities from the bloodstream of a human patient. But we can also do this to remove others, such as sodium hydroxide from cellulose products. Or microfiltration is where you would remove bacteria from drinking water. I think you may have seen like Life straws advertised. And ultrafiltration can be used for things such as separating the salt from whey out of cheese. We will be covering dialysis, but just to get you a flavor for the vocabulary, dialysis is the transport by a concentration gradient, so it's a mass transfer process, of small solute molecules through a membrane. Now, those small solute molecules that move across are called crystalloids. And the molecules that cannot pass through the membrane's pores are going to be the colloid. They're going to be small, insoluble particles. The feed that we bring in that contains these colloids and crystalloids is the dialysate. And the solvent that accepts the molecules, so where these crystalloids will move into, is called the diffusate. Now, dialysis will work best when the molecules in the dialysate are really different sizes, and so therefore they diffuse at very different rates. So those smaller particles typically can move through very easily. Larger ones don't move through, or not easily at least. Hemodialysis, as I say, is best known, but you can also apply this to recovery of other materials from liquid solutions. Gas permeation is using a non-porous membrane to separate gases. So you can take maybe a single component from air, or removing hydrogen from a gas mixture out of a reactor. Frequently, these use hollow fibers that are made out of polymer materials or rubber. This has been a method that's been in use since the mid-1970s. And you can look at the permeability of a variety of membranes in your textbook on page 847. Now, sections 13.4 through 13.8 of your book have a lot of different models for membrane processes. We absolutely do not have time to go over this. So I would recommend that you at least kind of look through it so that in the future, when you're asked to design a system like this, you'll have an idea of what kinds of information you need to gather before you can begin doing your analysis. The final little mini topic we want to mention is pervaporation. This is very, very closely related to reverse osmosis, which we will be talking about. In reverse osmosis, you have liquids on both sides. Pervaporation, you have a liquid on one side and a gas on the other side. It's really important that you make sure that your liquid stays liquid and your gas stays gas. So the liquid feed, you're going to maintain it at a pressure so that as you remove material, it still remains a liquid. So generally this means you need to keep that pressure high. On the gas side, you want to make sure that it stays a gas, and so we need to keep that pressure low, below wherever the dew point pressure would be for this permeate. Often this is a vacuum. We will be seeing in reverse osmosis that there's going to be a membrane that separates these two sides. It needs to be very dense and thin so that it can allow the molecules to move through, but what makes this a little tricky is it also needs to be strong enough for that delta P between the liquid side and the pressure side, or the gas side. So this concludes our little quick discussion of a variety of types of separation processes. We are going to come back and look at a couple of these with just a teeny tiny bit more detail. And then in class, we will be covering a few more where we'll actually start looking at the math models. Thank you very much for your time.